talk a little bit about Newton's form of Kepler's third law of planetary motion. Do some examples, basically an example where each of the variables is the unknown. Kepler's third law is set out by Isaac Newton, is very important in astronomy because it is going to provide the mechanism for measuring masses. And it's basically our only way of measuring masses. It is to see something in orbit about something else. You measure the period, you measure the semi-major axis, and you can get the combination of the masses of the two objects in the orbit. Let's go through everything that appears in here. So I'm assuming 4 is okay, and then pi is okay, so therefore pi squared is okay. So there's just this dimensionless factor of 4 pi squared. We also have big G, which big G is not little g. Big G, the universal constant of gravitation, and it takes a set value. As far as we've been able to measure, it's the same value everywhere in the universe for all times. So really, really a constant. And we are measuring things in kilograms, meters, and seconds. So if we do that, G takes the value 6.67 times 10 to the minus 11, and it is units of meters cubed per kilogram per second squared. And since G is taking this value, that is going to dictate what period has to be measured in, semi-major axis has to be measured in, and the combination of masses has to be measured in. So P is orbital period, and it is in seconds. If it is not in seconds, you have to convert it. A is the semi-major axis of the orbit, and that has to be in meters, and if it's not in meters, you have to convert it. And the masses, M1 and M2 both, are the masses of the two objects in the orbit. And that has to be in kilograms. If it's not in kilograms, you're going to have to convert it. All right. The first example I'm going to work through is a case where we're going to use Newton's form of Kepler's third law, the way it's most often used when we're trying to measure a mass. And the example is going to take some basic information about how our sun is moving through the Milky Way galaxy. So there's a top-down view of the disk of our Milky Way, and put a little bit of the structure in. So we are a barred spiral galaxy, and spiral arms coming off from the bar, and our happy little sun is sort of in the outskirts. There's a semi-major axis for our orbit, and we're going in a more or less circular orbit through the Milky Way. So from the speed of the sun and knowing where we're at in the Milky Way galaxy, we have measured that semi-major axis is 27,000 light years, and it takes us about 230 million years to orbit around through the Milky Way once. All right, so semi-major axis is in light years, but it's not in meters, so we have to convert it. The period is in years, and that's not seconds, so we have to convert that. So before we can apply Newton's form of Kepler's third law, we have to convert both of those. So we go and do that. So period in scientific notation, 2.30 times 10 to the 8th years. And 1 year is about pi times 10 to the 7 seconds. And I can tell that that's going to be a time in seconds because the year is canceling out both in the numerator and denominator. And that gives me 7.23 times 10 to the 15 seconds. And semi-major axis, 2.70 times 10 to the 4th light year, and 1 light year is 9.46 times 10 to the 15th meters. So just multiplying by 1, and a way to get the units the way we want, and light year cancels out with light year, so that's all good. That's going to give us 2.55 times 10 to the 20th meter. All right, so I've got a period in seconds, semi-major axis in meters. We're ready to apply Newton's form of Kepler's third law to measure the sum of the masses, m1 plus m2. All right, now I want to note m1 plus m2 here is mass of the Milky Way galaxy plus the mass of the sun, and the Milky Way galaxy has way more mass than just one average star, our sun. So that is pretty much just the mass of the Milky Way galaxy. Rearrange Kepler's third law. Mass of the Milky Way galaxy is going to be 4 pi squared a cubed over g period squared. We put in our values. 4 pi squared. I have a 2.55 times 10 to the 20th meters cubed. And then downstairs, we've got universal constant of gravitation, 6.67 times 10 to the minus 11 meters cubed over a kilogram second squared. And we need to have the period squared in the denominator, 7.23 times 10 to the 15th We want to just pause for a second and make sure our units are going to work out. I have a meter cubed in the numerator, meter cubed in the denominator. Once I square this second, it's going to cancel out second squared there. And so this is units of 1 over kilogram, which is just a weird way of writing kilogram. So that will work out to be a mass. When we do the calculation, I got that to be 1.88 times 10 to the 41 kilogram. And I'm going to say that that is approximately 2 times 10 to the 41 kilogram. Right. So that's a really big number. That might not mean much of anything. To try to interpret it and make some sense out of it, let's look at what the mass of the sun is, which also comes from Newton's form of Kepler's third law. 1.989 times 10 to the 30th kilogram. And that is approximately 2 times 10 to the 30th kilogram. So about how many stars are there in the Milky Way galaxy? Well, it's the mass of the Milky Way galaxy divided by the mass of the average star. So the number of stars, 2 times 10 to the 41 over 2 times 10 to the 30th, 10 to the 11th, which is 100 billion. So you might recall from like the first chapter, I talked about there being about 400 billion stars in the Milky Way galaxy. Where does that 400 billion number come from? Comes from calculations like this with Kepler's third law. No one is ever going to sit down and count 400 billion stars. And there's no need to. We can find out how much mass there has to be to account for the orbits of objects. And we know what the mass of the average star is, so that tells us how many stars they have to be. If we do this calculation a little bit more carefully and include all the way out instead of 2/3 the way out, which is about where our sun is in the Milky Way galaxy, we could come up with a more accurate number. But to the order of magnitude, this is already enough to tell us how many stars are in a galaxy like the Milky Way. All right, and do another example. And in this case, we're going to have the unknown is the semi-major axis. And we're going to do this for the Earth and the Moon. So there's the Earth, there's our Moon, and we want to know what this distance is. Semi-major axis. Given what we know about the period of the Moon's orbit and the masses of the two objects. So M1 is going to be the mass of the Earth, 5.97 times 10 to the 24th kilogram. M2, 7.35 times 10 to the 22 kilogram. So if I picked M1 to be Earth, then M2 has to be the Moon. And then the period of the Moon relative to the background stars is 27.3 days, which that's not in seconds, so we're going to have to convert that. There are 24 hours in 1 day. There are 60 minutes in 1 hour. And there 60 seconds in 1 minute. Multiply all those together, we'll get a period of 2.36 times 10 to the 6th seconds. And I can go through and check that that is going to be a time in seconds, because day cancels with day, hour cancels with hour, minute cancels with minute, so the only thing left is in seconds. So this is all set up correctly. All right. For an unknown semi-major axis, we're going to have a cube root. I have a period squared, universal constant of gravitation, sum of the two masses over 4 pi squared. And since Kepler's third law has the semi-major axis cubed, when I solve for the semi-major axis, I have a cube root. I put everything in for that. I've got 2.36 times 10 to the 6th seconds. I'm going to have universal constant of gravitation, 6.67 times 10 to the minus 11 meters cubed over kilogram second squared. And I've got the sum of the two masses. Going to give me 5.97 times 10 to the 24th kilogram plus 7.35 times 10 to the 22nd kilogram. And then downstairs I just have dimensionless factors, 4 pi squared, and to do the cube root I have to take this to the 1/3 power. And go through and, see, caught a mistake. That has to be period squared. Alright, so second squared cancels out the second squared from G, and then 1 over the kilogram cancels kilogram, kilogram. So I will have inside the square brackets something that's in meters cubed, which then I take the cube root of that, is going to give me a semi-major axis in meters. So I've got, so I go through and calculate all that, 3.85 times 10 to the 8th meters. Now, this mass of the moon is pretty small compared to the mass of the Earth. If I would just have dropped the mass of the moon, I would come up with an answer for the semi-major axis that's not very different. They agree in these first 2 decimal places, and then there's a difference in the 3rd decimal place. So this is an example where the masses are so different again, like in the first example, that you can pretty much ignore one mass compared to the other. Alright, and then the last example I wanted to do is what does Kepler's third law of planetary motion look like when it's the period that's unknown. So we're going to try to work out the orbital period. I have 2 identical white dwarf stars, each with a mass the same as the mass of the sun, which is not too dissimilar from what the average mass of a white dwarf is, and they're going to be separated by the Earth-Moon distance. We want to find what the orbital period for that binary will be. So M1 is the same as M2, is the same as the mass of the Sun. And that's 1.99 times 10 to the 30th kilogram. And that's already a mass in kilograms, so that's good. And then if they're at the Earth-Moon separation, we just worked out what that is. 3.85 times 10 to the 8th meters. So we have a mass in kilograms, we have a semi-major axis in meters, so the period is going to come out to be in seconds. All right, solving for the period, since it's period squared, this is going to have a square root in it. 4 pi squared a cubed over g m1 plus m2. Putting in values, 4 pi squared, 3.85 times 10 to the 8th meters cubed. And then in the denominator, we have universal constant of gravitation, 6.67 times 10 to the minus 11 meters cubed over kilogram second squared. And the sum of the two masses, 3.98 times 10 to the 30th kilogram. And that's all under a radical for the square root. And that gives me 2.91 times 10 to the 3rd seconds, which is about 50 minutes. So with all that increased mass causing stronger force of gravity, having two solar mass white dwarfs at the Earth-Moon separation, it's going to mean that they have an orbital period less than an hour. So instead of the moon going around the Earth in a month, we would have those two stars orbiting in 50 minutes. And a white dwarf star that has the mass of the Sun has a radius about the same as the radius of Earth. So those two white dwarfs could easily fit into that binary, and this is not unusual for what's called an ultra-compact double white dwarf binary. These things exist in the Milky Way galaxy. They're not the most common thing, but they're not all that hard to find either.